Today we're going to use another test method to help us determine the shear strength of soil. Remember from 2 weeks ago in the last lab, we have used the direct shear test to help us determine the shear strength parameters. And if you recall, the test setup was quite simple, and then the test itself was very quick. However, even if we can control the vertical load that we apply on the soil specimen, you have no idea what the lateral stress would be. Okay, so in addition to that, you cannot control the drainage of the soil, using the direct shear test setup. So because of these shortcomings, we are going to use another method to help us determine the shear strength of soil. Hopefully, with this test, we are able to control the stress states and then also the drainage of soil better compared to the direct shear test. So the test that we're going to perform today would be the triaxial test. This is a triaxial chamber, which you are going to use in a moment. So let us go through how we can model the stress state of soil using this triaxial device. So for example, at the site, usually the vertical stress and the horizontal stress would be different. So if you look at this schematic diagram, the vertical stress, total stress is 200 kilopascal, and then for the horizontal stress, total stress, it will be 50 kilopascal. Under a rest condition, usually the vertical stress will be larger. So how do you model this stress state using a triaxial device? So in triaxial test, basically the test is divided into 2 stages. The first stage is the addition of confining pressure. So suppose that this is the soil specimen. During the first stage, we will add the confining stress to the soil. So in all directions, the soil specimen will be subjected to the same stress. Using the example that we have from here, we can, for example, add 50 kilopascal of stress to the soil as the confining stress. So how about the vertical stress? So what we can do is, during the second stage, we can add the so-called deviated stress, delta sigma d, to the soil. So what we can do in the triaxial test is, while keeping the confining stress, sigma 3, we can add axially the deviated stress. So what you can do is keep sigma 3, and then you will add delta sigma d to the vertical direction. So based on our example, the deviated stress that you should apply would be equal to the difference between the vertical total stress and the horizontal total stress, which is equal to 150 kilopascal. So you will add this amount of deviated stress to the vertical axial direction, such that you will achieve the stress states that you have at your site. In addition to that, when you perform triaxial tests, you can control the drainage. So remember that from direct shear test, you have no control on the drainage, so you do not know whether you are basically shearing the specimen drained or undrained. It all depends on the permeability of the soil. But for triaxial tests, you can specifically control the drainage. So there are several types of triaxial tests that you can perform. For example, when you apply the confining stress, you can open the drainage valve such that the addition of confining stress would come with drainage of water out of the soil system. So we will denote that as C. Alternatively, you can perform an undrained test during the addition of confining pressure. So for that, we will denote that as U. During the second stage, when you apply the deviated stress, again, you can choose to allow drainage or disallow drainage. Okay, so you can have a drained situation and undrained situation. Okay, so based on this test matrix, we can have several combinations for the triaxial test. For example, you can have a consolidated drain test, you can have a consolidated undrained test, you can have unconsolidated undrained test. Okay, you should also have a unconsolidated drain test, but this test is seldom performed because if you close the valve, okay, if you do not allow drainage during the addition of confounding pressure and allow drainage during the addition of deviator stress, basically you do not know whether the drainage during the second stage is due to consolidation or shearing. Okay, so because of that, UD test is seldom performed. Okay, so we are mainly dealing with CD, CU, and UU. So depending on the soil type, okay, CD test can be very long. It takes a lot of time. So imagine that if you have a clayey soil, which you have a very low hydraulic conductivity, what you would expect is it will take a long time for the consolidation to complete, and then also you would have a long time for the drainage to complete during the shearing stage. Okay, so CD test will take a long time if you have a material with a very low hydraulic conductivity. So in this lab, okay, that you are going to perform today, we are going to use UU test because it is relatively quick and then relatively easy to handle for students who have no experience. So we are going to use UU test. In fact, what we're going to have would be a special type of UU test, which is called the unsaturated, unconsolidated, and then undrained test. Because remember, 1 month ago, when you prepare a soil specimen, we have, which is here, okay, we are going to use this soil specimen, and then we are not going to saturate the soil. Okay, so what we are going to do today is a UUU triple U test. So based on the mole Coulomb failure envelope, what you would expect is if you have unsaturated soil specimen and if you perform unconsolidated undrained test on the soil specimen, then what you would have is if you look at this shear stress and normal stress diagram, what you would expect is there are several Mohr circles. Each of them represent a certain degree of saturation. Then if you connect, okay, if you connect the Mohr circle together, you will have basically a linear relationship like the Mohr Coulomb failure envelope. You will have an intercept C and then also a slope, okay, which is the slope friction angle corresponding to unsaturated, unconsolidated, undrained test. But if you have a saturated, unconsolidated, undrained test, and if you perform the test, what you would expect is the friction angle corresponding to those specimen would be equal to 0. Okay, this should be discussed in your soil mechanics class. So we will use what we learned from that to calculate the C and then also the phi for our soil specimen today. One more thing that we can observe when you observe the triaxial test is to observe the failure states of your soil. So what you will expect is from your soil specimen when it fails, okay, you will see a failure plane. Okay, you will see a failure plane, and then based on the Mohr circle at failure and then also the Mohr Coulomb failure envelope, what you can derive is the angle of the failure plane, and then it should be related to the angle of your friction angle of friction. Okay, so the relationship is 45 degrees plus friction angle divided by 2. That would be the angle of your failure plane. So in the next 10 or 15 minutes, your TA will demonstrate how you can set up the triaxial device and then also help you test the membrane to see whether it is okay to use. because you will need that to wrap up your specimen. Okay, so your TA will take over and then go over the setup with you.